So, hi everyone, I'm Viviana Marquez. I'm the AI community lead here at Prolific. And in case you haven't heard of us before, we're the platform that connects AI researchers and developers to high quality human data in hours, not weeks. That's my favorite part. So if you're wondering, this space is part of our ongoing series, exploring the ideas and research shaping the future of AI. So this is a casual space, a place for us to dive deeper into the work that is pushing the boundaries in how we understand intelligence, learning, and also human-machine interaction. So as I was mentioning earlier, we'll start in a couple of minutes while people join the room. In the meantime, I'd love to hear from you. Tell us in the chat where you're joining and what your role is and what are you interested in learning. And for those of you that are joining, I see the numbers going up in the call. So for those of you that are just joining, we are just doing the introduction, so you haven't missed anything so far. But if you want to share in the chat where you're joining from and what your role is, that would be great. All right, so we have a few people joining us from IBM, from San Francisco, cloud researchers. Nice to have you all here as well. All right, so the way this webinar is gonna work, it's gonna be 45 minutes, give it or take, of conversation. If you have any questions for our guest, feel free to drop them in the chat throughout the session, and we'll gather those questions for the portion of Q&A towards the end. So with that, I'm really excited to welcome Dr. Bo Wen, staff research scientist and AGI expert at IBM. His work sits at all the hot topics right now, at the intersection of Gen AI, LLM reasoning, multi-agent systems, and human AI interaction design, exploring how intelligent systems can reason, collaborate, and adapt more like we do as humans. So everyone is talking about the next big leap in AI. Since 2022, when ChatGPT came out, the general public had access for the first time to AI without having a specific higher degree. And we've seen how powerful it is, but LLMs are still very limited. They're limited to human preferences. So that's a big topic today. And we're gonna talk about how do we move towards something closer to genuine understanding or even superhuman intelligence. So if those topics spark curiosity, you're absolutely in the right place. Dr. Wen is the author of the paper, The Missing Reward, Active Inference in the Era of Experience. And this is a fascinating conceptual paper. So if you haven't read it, don't worry. We're going to be talking about it here today. But also, you should read it after this webinar. So in this paper, Dr. Wen takes a bold look at how we might build these AI systems with a richer sense of agency and self-directed learning. So I'm really excited to unpack this paper today. And I want to start with the last sentence of this paper that I thought it was a big, big sentence. So it says, the era of experience may prove as transformative for AI as quantum theory was for physics. So for the physics fans in the room, you can feel the enormity of these words. And the way this will happen will be not through brute force scaling, but through deeper understanding of intelligence itself. So with that, I just want to give a big and warm welcome to Dr. Bo Wen. Thank you so much for joining us today. How are you doing?
Good. Thank you, Vivian, for the opportunity and allow me to join this discussion with you. And hi, everyone. So where should we start, Viviana?
Yeah, maybe let's kick off things on a lighter note. I saw that you went for undergrad, you studied physics, and then you got a PhD in physics and a postdoc in physics, but now you're working in AI. So I'm just curious, how did you find that way from physics into AI? Was there like a particular aha moment or a question that drew you into this field?
Yes, actually, it starts with some, I would say, painful experience. So when we were in physics, when you're a PhD student, one job my mentor gave me is you have to read a lot of papers every day because there's a lot of great researchers around the world doing all kinds of studies, and there's new discovery every day. And that's the fantastic thing about our time. The information is exploding, and we can get instant information through the internet. But that become overwhelming sometimes because you cannot just keep up. It's just impossible to keep up with all the things happening. And I, as a physicist, I start to think about that problem itself. And then I realized that's also a physics limit of our communication bandwidth of our brain because there's only 24 hours a day and we can only read that fast. But there's thousands, if 10,000 other physicists writing paper all the time. So the combined writing rate is faster than my reading rate. So I will never be able to catch up with all the things. So then I happen to be in IBM in a digital health group. I have a lot of colleagues around me study neurological system of human brain and our spinal cord. So the idea of a brain-computer interface came to my mind. I thought, okay, then maybe before I can make any or for the whole world to speed up the research, we need to figure out a way to speed up our bandwidth of reading. So I started looking into how human brain works, and for many years, so I studied that's how I evolved to today. So AI is part of my research, but more generally, I guess in the past the word is called cognitive science. I study how intelligence, natural intelligence like us and animal, but also artificial intelligence, how intelligence work in a more general high-level sense. So there's a physics laws governing how information transmit and how we manipulate information. So to me, AI, the study of AI is still part of the physics world. And so, yeah, that's where I am today.
That makes sense. And what you were saying totally resonated with me. I live in San Francisco, and the other day I overheard someone on the street saying, "Oh yeah, I'm not up to date because I haven't checked the new features of Claude Code in the past 2 days." Something like that. It's
Right.
just moving so fast. And speaking of the field moving so fast, and maybe this is the teacher in me, but I like to take things from 0 to 100. I know that we have a very diverse audience right now. So before we do a deep dive, maybe we can start with the basics and make sure everyone is on the same page. Would you be able to give us a high-level understanding of how current large language models work?
Sure. So actually there are several phases of how the AI evolves, right? The current language model, the most naive way to understand its behavior is just doing a very simple job. It's trying to predict the next word based on what it sees before. And but in order to do this job like very well, like today's large language model, it's actually a very complicated mathematical and probability problem. Because the first thing is it's actually similar to how we handle language, because I hear what you said and I hear myself saying some sentence. So my brain is constantly maybe consciously or unconsciously thinking about what should I say next. And sometimes we make mistake, and then I go, okay, I need to rethink about it, and then it's to be something else. But that's how our brain works as well, in some sense. But we doesn't like consciously thinking about the process. We kind of like automatically do it, and that is done through practice. When we were young, we learn how to speak from our parents, from our teacher, and then slowly we learn grammar. So in the 50s, people saying, okay, all of this is just rules, mathematical operations. So in the 50s, the AI community is trying to build chatbot by using mathematical rule. But then they found that, okay, with all the if-then, you need to write tens of thousands of if-then logic to handle all the situations, and that's just impossible engineering work. So then it doesn't work out that way. And then many years passed, there's a lot of different things got discovered. One important thing is, I think 10 or 20 years ago, people start understanding what's the right form to represent language is using vectors. So there's a famous paper called Word to Vet. Essentially, it's use a vector representation of words, and then some of you might see this. So once you do that, you can have a space representing concepts. For example, if you measure the distance between man and woman and king and queen, you will see the distance actually is similar, and the vector pointing to the similar direction. So this gives you a way to use mathematical operations to navigate through the concept semantic space. And then later, people learn how to use a neural network to automatically generate, to do those calculations. And then another important paper is Attention is All You Need from Google, and that really ignites the current AI wave that we are seeing right now. At that point, these models learn, okay, not all the words is equally important. They learn how to pay attention to the important part of the sentence, or you can say information in general sense. And then once you do that, the sentence it generates becomes to make sense, because now it follows the common sense, and it also resonates with what's going on in the context beforehand. And now the probability of picking all the words become more accurate. And that's how we evolve today. So all the language model, what it's doing is it's just looking at all the text comes beforehand, and then trying to predict what's the most sensible word to output in the next, and voila, we have something.
Yeah, I find it
amazing.
Fascinating how neural networks are able to come up with some math to represent words and concepts and meaning in a numerical form. I've studied the math, and it still blows my mind that we're able to express language through math and do math on language such that it produces a language that is very similar to how we speak. So much so that people might mistake to believe that the LLM has intelligence on its own, but in reality, as you were mentioning, it's just predicting the most likely outcome given of what you said. Right. Maybe in there, I would want to give our audience a little bit of context, because if you're just trying to predict the next word, the sentence might make sense, but sound a little bit like dry. But right now, if you chat with, for example, ChatGPT, it sounds very natural and very conversational. What was the secret sauce that led to that conversational component?
Right. So this goes deeper. Actually, so there are several things happen that makes this possible. One is OpenAI figure out that you can use the whole internet as the training data to pre-train the model. So actually, the model learns all the different ways of expressing similar ideas, and then there's other study that they call personality of the model. So inside the model, they found like if the model have different neural paths, and it picked the different neural paths, it will speak in a different way because it sees all the different ways of speaking things in its pre-training data set, the text got from internet. But then this decision making is actually now become the secret sauce or the core technology of how to make the model behave in a way that we prefer, right? So how to tune that is actually not easy because there's no single knob that allows you to change the behavior. Now you have like a huge matrix of the model weights is like a huge matrix, and then to change its behavior, you need to change a lot of numbers in it, and no human understand how to do that. It's just like we don't neural nurturing understand how all the neurons in our brain actually wires together. It's just a massive neural network. Let's just put it that way. And the engineer way of doing this is through fine tuning. So reinforcement learning has the concept of if you from the output you can give it punishment and then that's a signal to let the network. So the network give out like 10 different answers. You can like give ratings, and then that's become reward signal, and then somehow through the algorithm it will feedback and then change some of the weights to make the model output some of the things that we prefer more likely. So it increased the probability of outputting those outputs, and that's what we call reinforcement learning from human feedback. So then we have a lot of people trying to just give ratings to the model, and then slowly the model's behavior will change. So that's how current practice is doing. But of course, this is becoming a labor-intensive industry because the model is trying to do more and more work, and you need more and more human to watch out what the model is doing, and then the model is not like our kids that, well, our kids, even my kids, he doesn't listen to me all the time. So maybe the model is indeed like our kids. So when you give it all this reward signal, sometimes it works, sometimes it doesn't work. Sometimes the model still behave the way, in a mysterious way that we call hallucination, right? Sometimes the model make mistakes. So that's a frontier research topic that that the whole industry is still trying to figure out.
Yeah, exactly. So I've seen a lot of researchers talking about fine-tuning, and now some people call it post-training, mid-training, and all the different trainings. But at the end of the day, the reason, and of course feel free to add on to this, but the reason why they're so conversational is because they are being reinforced by these human preferences. So for example, when people are using ChatGPT and they ask something, and then ChatGPT says, which one of these two answers do you like better? And then you click one of those, the GPT model is taking that information as a signal to improve and become more conversational. But let's build on that, and now let's build on that while switching gears a little bit. So in your paper, you reference the era of experience paper. So this is a term that was first introduced by David Silver and Richard Sutton from DeepMind. And they basically describe a shift from this because all of these data sets are static. Us as humans, we don't learn from static data. We learn from or dynamic experiences with the world that we live in. So this paper talks about that, like how do we get agents to learn from dynamic agent-generated experiences? So maybe we can start from there. What does it mean for an AI to learn from experience, and how is it different from the current paradigm?
Yes. First, I would like to express my how do I say, my respect to Professor Richard Sutton. for those maybe who we have some audience, I don't know. For those who don't know who he's the father of reinforcement learning. So he has a blog. He has a personal blog, and there's one very famous blog from him from many years ago, the Bitter Lessons. That's almost becoming the Bible for the AI community, research community today. So so everything he says, we listen. Let me maybe explain a little bit why this is important. So like I say, in 50s, people try to use try to really explicitly write down rules, because at that point people of course at different times people's ideology changed. At that time people really think logical, like explicit mathematical rules are the king, right? So they try to build AI through that way, but then they realize it's impossible to write down all the rules of the world, because the world is just changing and it's very complicated. So reinforcement learning is the idea of okay, if we cannot write down all the rules, we can try to mimic how kids learn from things, right? So we just tell it, okay, this is right, that's wrong, and then let it figure out what is the hidden rules behind the scene. So that's the core idea of reinforcement learning. So you just create a loop, and then it's a self-feedback system. The model does something, and then you give the reward, and then it will try to do it again, and then slowly the model behavior will go towards the place that you intended for it to go. So DeepMind is Google DeepMind is the research lab. Their biggest how do I say? They are the experts in reinforcement learning.
They're one of the authorities. If they say something, you listen.
Yes. So AlphaGo is from them, right? And so all of these they demonstrated the power of reinforcement learning. It's just a very fascinating method to build AI models, to train them. But sorry, I kind of forgot. You have a question about this. I kind of drifted away. What was your question again?
So we were talking about the era of experience, and maybe to set the ground. What does it mean for AI to learn from experience? Because I remember the first time I heard about that, it kind of sounded like science fiction. I was imagining like a robot on the street, just like learning from experience. What does it actually mean? At least nowadays, maybe in the future it's going to be like that.
Yeah. Okay. Very cool. This goes back to the human reinforcement learning from human feedback, right? So today all the models is do pre-training, and then we do this fine-tuning afterwards. But then there's another thing called scaling law in the AI world. So essentially what it says is with the more data and with a bigger computer, the model performance will improve. But then at some point, people realize actually the data is not infinite, because we exhaust all the OpenAI already exhaust, and not like all the big AI large language model companies. We kind of exhaust all the human written text in the past few thousand years. Like the fossil fuel is gone, so there's no more human generated data to train model. And then does that mean the model performance will just saturate and get capped at there? That's a problem, right? And then that's when this era of experience paper come out. It points out that using human data to do this large scale pre-training is just not sustainable. It's not like a thing that we can do forever. The more practical way or more natural way to train AI is to let it learn from its own experience, just like us. So think about our kid. All of us went to school. So there's only so much things you can learn from school. from the book. In Chinese, actually, there's a very good sentence. Let me think how to say. 书上读来终觉浅，觉知此事须躬行. I think that's how it. I'm a little bit rusty with my Chinese, but to translate it, the meaning is when you try to learn something by reading a book, in the end you will still feel like your understanding is shallow. To really understand, to master the skill, you have to like get up, do the work. This is meant talking about things like, I don't know, like if you try to build a IKEA furniture or something,
Totally.
or learn to drive a car, you cannot just by reading. You have to go there and use your hand and actually do the thing. Or any sports, like you can never learn how to play football by just reading the book. You have to be there.
I tell that to my students all the time. I teach coding, and I'm like, if you watch me code Python, you'll never learn how to code Python. You have to go out there, make mistakes, and next time you're gonna remember from your own mistake and correct it and do better. So you have to do it yourself. So basically, we're trying to get AI to do the same thing.
Exactly. That's the core. That's the idea of that paper. Is saying you have to learn through your own experience, try and error, and then learn and then remember what you did wrong and what you did right, and that itself gives you the reward signal for you to change your behavior to do better next time.
Yeah, I thought it was super interesting how in that paper they reference current LLMs being limited by human intelligence. Well, not human intelligence, but by human preferences, because they're being fine-tuned on these preferences whenever they ask the user, which one of these two answers do you prefer? And what if we wanted to achieve superhuman intelligence? And in the paper, they mentioned systems like AlphaZero and AlphaProof. So AlphaZero basically focuses on being really good at playing chess, Go, and these games. And AlphaProof, same thing, but with math. So basically, they're given a specific set of rules. They learn the rules, but they're not given any human preferences. They just go out and explore. And because of this, they have reached superhuman performance through experience in this field. So, for example, AlphaProof was able to win a silver medal in the math Olympiads without any human intervention, just by knowing the rules of how to do mathematical proofs. But something interesting is that those two examples that I just talked about happen in close, well-defined environments. And as you mentioned in your paper, for example, something like human values. Human values are not close and well-defined. They evolve with context. It depends on the different cultures. It might change with different experiences and learning. So I guess my next question is, how do we design agents that can incorporate that experience learning on fields that are not closed, like mathematical proofs?
Yes. Actually, we can use another analogy to understand this. Think about when we go to school, right? There's kind of like two camps of it's natural science, like math, physics, chemistry, biology. That's normally nerds like me who doesn't talk well go to those schools and then deal with objective things that like math, like there are single solutions within a certain set of rules that doesn't change, and you will know you will get to the answer by just keep working on it. And then there's the other camp is social science, right, dealing with politics, religions, and all this human nature. And over there, I would say, to me, I feel like that's a more difficult place to be because the rules is not clear, it's fuzzy, and you have to deal with things in the context at the moment. And there's no thing. It's not like physics. Once you figure out something, you know it's forever it's going to be true for the rest of the age of the universe. But when you deal with human, they change all the time. So that's.
This is making me. No, I was gonna say that this is making me laugh because that's part of the reason why I studied mathematics in undergrad, because I like things that are concrete. But look at us now here in AI talking about this very flexible and ever-changing context. So you can't escape it.
Yes, exactly. The thing is, human society is wonderful because of all the changes all the time. Like we are not like rocks that just sitting there and then doesn't follow the physics rules of gravity, just sitting there and doesn't change. That's a word with that word. It's not a word of life, right? The word of life is just the constant changing is the part of the beauty of this world. So we have to deal with it in the right mindset, and that's where this Now let's talk about how AI deal with this, right? So when you train an AI model, try to solve like the math and physics problem, you know there's a one single right answer in the end. So you can just let it try, and with enough time, hopefully it will. You can even just do brute force. If you have enough money, just plug in the computer, let it run forever. Eventually, it will give you the right answer. But of course, that might not be the most economic way to do things. But now we need to build AI chatbots to live in the human world, to serve human in all other areas. Like for example, my day job is to build medical chatbot for patients to do psychiatry, to help them with their mental health problems. So over there, you have to really understand human emotions and all the concepts and backgrounds of what's the life struggle they are going through, and that's not that's not science. There's no single right answer there, and that's why this human reinforcement learning with human feedback kind of breakdowns here a little bit, because if you think about how the model is serving today. There's one model live somewhere in the cloud, and then its way is fixed, and then it's serving all the people talking through the chat interface at the same time, and maybe 10 people click they like the thing on the left hand side, and then there's 50 people click they like the thing on the right hand side. So if there's all of these people expressing different preference, then in the end, how are you going to decide where you go? If you only go with a majority, then actually the US voting system tells you that's not the right way to do things. You cannot just always go with the majority, because that's just brutal. It's not humane. And you have to do the, I forgot what's the right political terms, but in American, I think they give certain votes to different states, and then you have to every state, based on population, you have some votes, but it's not purely based on population. You also have a different district. So ensure all the people's opinion have some way of being heard and then being respect. And that's a model today's AI operation practice is not able to take care of, because maybe every night at 12 p.m. We collect the data for the whole day, and then someone in the server room click a button, and then the AI model starts training to do fine-tuning from today's preference. And then tomorrow do this cycle again. It's very static, and then the signal is mixed. So the model, I think, if I imagine the model is a human, like imagine how it works, is like, okay, now I get all of this very complicated mixed feedback. So how should I behave tomorrow? If I behave in a consistent way, then I'm going to piss off half of the population for sure, because I'm behaving like the other half like. So I cannot please everyone. So the only way for the model to actually please everyone is it needs to have multi-personality, and it needs to know who he is talking to, and then try to be the person that person likes. And now it becomes a judgment problem. So how do I know this user open a chat window, start talking to me? How do I know what he likes? So I need to know something about this human in order to understand its preference. And this data is not available to me. And that's why this model starts to, if you go down this rabbit hole, it become a, how do I say, it become like an engineering rabbit hole. It just, I don't know whether there's a
Yeah,
way to
you're
solve
always
that.
like chasing how to optimize for that preference, which I think is an interesting problem, because for a while the problem was how do we find data to train our models, and we need more data. But now in this new era of experience, the bottleneck seems to be how do we define that reward such that the model or the agent can learn from the experience. So I love that you mentioned the judgment dilemma problem. So we can tie back to your paper. In your paper, you're proposing, well, how do we solve this bottleneck about the reward creation through active inference? So maybe if you can, for
Sure.
people in the audience that have never heard about active inference, tell us a little bit more about that.
Okay, so then let's talk about active inference. So active inference actually comes from Professor Carl Friston. So he's a neuroscientist. He has a very successful work dealing with I think it's a psychosis in his neuroscience. And then through there he realized that there is something common in all the life form. In how he's dealing with patients, right? But from there he understands psychology and how human brain works, and then he figure out, okay, actually there's a bigger, more abstract universal law that can describe the intelligence behavior, which has something to do with physics, the free energy principle. Concrete. Let me try to. So there are several cornerstone theory that he's building on. There's a Bayesian inference from the statistic. So essentially, it says how we make decision is based on probability theory, and then just like how LLM trying to predict next word based on probability. So because once you use probability instead of explicit mathematical rules, then you can deal with fuzzy situations. So that's one part. And then other parts is the free energy principle, which is minimizing free energy is the goal. So he unifies perception and action through this series. What it says is all the life being, there's a universal goal sitting on the very top is to minimize what he call free energy. And his contribution is he write down the mathematical form of the free energy for perception and for action. So for I'm heavy here. Let me just read it so that we are being precise. So variational free energy governs the perception. It has multiple forms that connects back to the physics original free energy in the physics terms. But then through transformation, mathematical transformation, he proves it can break down into the model complexity minus the prediction accuracy. What does that mean? The meaning of that is when the agent sees something or have some sense signal coming in, it tries to predict what does that meaning for it. So it needs to use a model to explain the phenomenon. Let's give an example. For example, I see something on the table. I need to decide what is that thing, right? So based on the color, the shape, I can say, okay, that's a book because it's not moving. But then in very rare case, maybe in Harry Potter's world, the book starts to talk to me. Then, okay, now there's a new observation I got. So I need to explain, okay, with this new observation, what's happening? Is it that the book is a magical book because it starts to talking? I know that normal books doesn't talk, right? So I need to have a model to explain all the things that I observe, and the model. And to minimize free energy means I need to use the simplest model to predict what I'm talking, my observation. I can go with a more complicated model, but if the accuracy doesn't increase, then the more complicated model is just increase the free energy without benefit. So normally, most of the time throughout our life, actually, I think maybe in different culture there's different ways to say, but our parents always tell us, or our managers always tell us, don't overcomplicate things. If there's a simple solution or a simple way to explain things, normally that's the right way. And actually, I think there's a theorem called the Razor theorem. It just says normally the simplest explanation is the right explanation for whatever you see. So that. Yeah, exactly. So there's many other, discovery or many other people confirm that this minimizing free energy is the correct way because we all experience the same thing. Okay, so yeah, that's a very brief explanation of what free energy principle means.
Yeah, I thought it was a very interesting framing because so far a lot of the researchers, what they're proposing is maximizing that reward so the agent learns from its experiences. But in your paper, you're proposing minimizing the free energy, so basically minimizing the element of surprise. So the model expects something, and then if it experiences something differently, it needs to adjust. And I think for me, the aha moment came when I realized behind this is just Bayesian inference guiding these principles. So maybe just being mindful of time and going a little bit into the nitty-gritty details of your paper. You mentioned that, there's a lot of mathematical constructions in there, but the one that particularly caught my attention was something called the C matrix. So the C matrix is the one that captures the priors of this Bayesian inference, so the original preferences. And I have a question that I know it's an open question, but maybe I would like to gather your thoughts. How would you say is the best way for researchers to make sure that the agents don't arrive at the wrong conclusion? How can we ensure that these autonomous agents, while they're forming their own objectives, they're also still aligned with human values and intentions and ethical boundaries, of course?
Yes, yeah. We gave a very brief introduction of free energy just now. So maybe let me explain what C matrix means. So C matrix actually is a term inside the mathematical formula that represents the agent's preference. What preference means here, we need to explain another thing. So what we explained just now is called variational free energy. Essentially, is how the agent explains what it sees. The sensing is the perception. But besides perception, the agent needs to interact with the world, doing action. So in action, there's another called expected free energy. Essentially, it's I can decide going left or I can decide going right. So how do I make judgment which side I go? And the goal here is I need to minimize the future surprise. So I still need to minimize free energy, but I need to plan ahead and try to estimate which parts is going to minimize future surprise. And this is easy to understand, right? So like whenever we are driving, there's several ways to go to my office. I need to decide which way to go. Before Google comes out, I need to based on the last 10 days, my experience going left has less traffic and going right there because there's a school bus stop. I probably run behind it, and then it's going to make me late. So this is my model prediction. But then there's a surprise coming up. If one day I going left, there's a road construction, and I got stuck there, right? So how do I minimize this surprise to coming up to me? I need more information, and so the expected free energy has two terms. One is information gain. The other is called pragmatic value. The information gain means if I do something that can tell me more information, those information is going to help me make better decision in the next step. So I should take a chance to gather information. But if I focus solely on getting information, I will never get my pragmatic value, which is where I actually want to do in the end of the day. So it's kind of like we going to school, right? So going to school is the time we spend to learn more things. Okay, maybe it's not the right life advice, but for a lot of parents, they are telling kids, okay, if you don't go to school, someday you are not going to get a job, and you become I don't know how our parents. That might not be the right way, but that's what most parents does. So going to school is to gain information, but in the end, the goal is to get a job someday. So you need to balance these two things. If you just stay in school forever, like me, I spent how many 20 years in school because I do my PhD and postdoc, so a lot of time in school. By the time I get a job, I'm already 30, and my parents was very worried. Okay, are you going to survive for the rest of? But in the end, it pays out because all the knowledge I learned in the school actually helped me do my job better. So actually, I get a better job, and eventually, I arrived today and have a happy life. So my pragmatic value got realized, even though it takes a bigger, longer time. But if I just stay in school, just only learning and never come out to do what I actually want to do, then obviously that's not the right way to do things. And if you just like a quick action, you only chase after your pragmatic goal, you never gain information. Sorry. That's a lot of times the mistake we made when we on stock market. We didn't do enough research. We see some stock going up, and then you say, okay, I'm going to buy. And then next second, it starts to crash, and then you got stuck. So apparently, you need to balance these two goals very carefully. And the C matrix is a part of the pragmatic value. So it's a matrix in code, what's your personal preference? Where is the place you want to go? And in terms of AI, if someday we build an agent based on active inference, that's where we can tune to control the behavior of the agent to align with our value. What does that mean? Essentially, is when we grow up, our parents and our school teachers is telling us what's the right thing to do and what's the wrong thing you should avoid, right? And all of those knowledge is somehow encoded in our brain, is the part where the C matrix is presenting. So whenever we decide, make a judgment, so tomorrow what I want to do, okay, we need to give some dramatic ideas here. Okay, for example, if there's a shady way of doing something like, let me see. For example, okay, going to a store, if the shopkeeper is not watching, are you going to pay for the bread you take or not, right? So that's that's the value judgment there. So our parents tell us you should never steal. You need to be an honest person. Like you pay for what you are trying to get, right? And over there, we will make the judgment. Okay, I shouldn't do this because I'm an honest person. I need to align my behavior with I believe who I am, right? So that's the pragmatic value there, and obviously if you don't have that principle in your head, then you may behave in a different way, and so that's how we like how we teach our kids. We teaching their behavior not by constantly watching them, It's because nobody likes the big brother keep constantly watching what you are doing, right? The right way of education that at least the modern society believes is we teach the value system to the kids to have them shape a good value system so that we don't need to watch them all the time and we know they will behave honestly and being good citizen for the society. And the value system that we are talking about in the school system is the C value in this mathematical form here.
Sounds good. So maybe last question from me, and our audience can get ready to ask questions. So feel free to send the questions while I ask my question. So maybe, and maybe this is the mathematician in me, but I'm more curious about how does this C matrix look like? Is it like key values pairs, and then it's like a possible scenario and the reaction, or how does it actually look like?
Actually, we say it's a matrix, but actually the mathematical form is a vector. Active inference is a form of Bayesian inference. So if you look at the math, essentially it's actually an array, and then in the array, I guess there's a you can think of this for example. Okay, think about this in terms of LM, right? In the end of the day, you try to predict the next word. And then this is an array that you times to there, and then you will change the probability of all the words. Essentially, you're changing the probability of the choice that you do in the next step.
So, okay. So it's a matrix of probabilities of what you're gonna do in the future steps, right?
Yes. So there's multiple ways to implement active inference mathematically. There's a metric. The common practice is there's a matrix way, but then over there the engineer have to like specify the value in the matrix. So you define, okay, if the first box means doing something, and then you assign a certain value to it that encodes the preference. But that's obviously not a sustainable engineer way to scale the system up. We kind of like going back to 50s. And that's something active inference got critiques from other AI researchers. So I think right now the research is trying to figure out how do we use reinforcement learning, deep learning, neural network, and all of these modern techniques to make this Bayesian inference to work better. So actually one of my current research is how do we use transformer, so essentially the underlying technology for large language model, to do active inference, and then we can leverage all the AI infrastructure and all the new mathematical tools to do this model in a more efficient way.
So if I'm understanding correctly, right now those priors are captured by the engineer, but hopefully in the future these are like values that are initialized at random, and then through some deep learning architecture you'll be able to find the best values.
Yes, active inference is still a very new theory. So right now, a lot of the research still stay on very you would say toy problems, like in a small Greek word, and then you essentially it's like a little game. You have an agent walking in a world of boxes, and then you can see that it's actually doing the right thing like you expect. But then to scale that model up, we need some more. We need to grow the community, let more young people come in, join us, figure out the more ingenious way to do this in a large scale way, right?
Yeah.
Actually, I'm going to Montreal next week to join a workshop of. There's an annual workshop for active inference this year. Actually, is in Montreal next week.
Oh, fantastic!
So we'll see other researchers.
for those in the audience that maybe want to deep dive now, there's a conference in Montreal. So truly fascinating. I think the LinkedIn comments are a little bit delayed, so I'm just giving it a little bit of room to see if they come through. But sure. I guess last question, and this one is more on the speculation side. Now we're going to be able to work in the near future with these AI agents that have intelligence potentially, eventually, superhuman intelligence. What do you think it means for us as humans to work next to these agents, and how can we work with them responsibly?
Yes, great question. So actually, I think it's a decision that will. It's not a purely decision on us. It's also how these AI agents will evolve. You mentioned earlier that the sci-fi version of having robots walking on the street, right? So that's actually something, I don't know. It's something the decisions is in humans' hand. Is how are we going to engineer these agents? Are they going to be like the bad version is in the movie Terminator, the Skynet. Essentially, is a centralized agent, huge supercomputer, single super mind, live in the cloud. Or it can be in many other kids movies. It's like individual smaller agents, and then each agent is kind of like human, have their own behavior, have their own life or experience, and then they live like just more like us as a society. So it depends on how this model is going to evolve, and that's a question we don't know. We cannot really predict the future yet, and I think actually it somewhat depends on the economics or the business of this industry. Because both ways has its pros and cons, right? So the centralized model essentially is easier for the engineer to maintain the system, right? Everything is in one place. But we have the problem of that we mentioned before. It needs to have multiple personalities live inside the model to deal with different systems, different situations. And in some sense, it's also wasteful because it needs to learn to be a physicist, but it also needs to learn to be a doctor or a mathematician. And every time when it deals with one task, it's only using a very small part of its weight, and all these other weights is just sitting there. Actually, okay, let me maybe make an advertisement for my old company, IBM. So IBM kind of like believe in the other way. Is the small model path. Essentially, we will have a lot of different small models, and each small model is specialized in some domain. And then you can personalize this. You can customize this model for the specific task, so it's more economic to run. But then, on the other hand, the problem is how do you maintain this? Right now, the small model path will cause a lot of engineer overhead because now you have more models to manage. But if I think like time will prove, if we go down this active inference way, if each model can learn through its own experience in a more autonomous way, then the small model path, of course, is going to be more economic prefer, and then it will prevail in the future. And at that point, actually, your company probably will become the school system for these small models. So instead of doing choosing left and right like today, it will be you will giving a class or maybe giving a seminar, webinar like us doing now to all these models, and then to just pass on the information, the knowledge to them, and then they will learn like our kids just through interacting with the world and with others, and then they will watch over each other in a responsible way to form a society and become part of our society.
That's fantastic. Thank you so much for sharing those thoughts and that vision. I'm a teacher, so I really hope I get to see the day where I'm teaching actual AI bots, however that looks like. Thank you so much, Dr. Vo, for joining us today. There's a couple of questions in the chat. However, I do want to be mindful of time. We're going over 1 minute. So maybe we can address those directly on LinkedIn. But yeah, this has been a fantastic conversation. Thank you so much for taking the time to doing this deep dive about the future of AI with us. I think just to conclude, what really stands out is that vision of moving beyond just brute force scaling towards systems that understand and explore and adapt in ways that feel more alive. And precisely at Prolific, that's what we care about. We care about building the infrastructure that keeps human insight, ethics, and creativity at the center of AI development. Because even in the era of experience, it is human experience that ultimately gives these systems meaning and direction. So yes, thank you so much, Dr. Vo, for sharing your time, your ideas, and your work with our community today. And thank you to everyone that joined us in the chat on LinkedIn and on Riverside as well. So if you'd like to keep exploring these topics, make sure to follow us on LinkedIn or our website. And until next time, take care, stay curious, and keep exploring the future of AI. Thank you so much.